Imagine you're running an F1 pit stop. Literally, a fraction of a second is the difference between spraying champagne and a crashed car. There's zero room for hesitation, zero room for fluff. Well, in your Cambridge IGCSE Physics exam, your digits, the exact numbers you write down, they are those fractions of a second. Welcome to the explainer that's going to tune your exam strategy to absolute perfection. Let's jump straight in. So let me ask you, would you bet your final grade on 1.2 or 1.24? Honestly, to the untrained eye, they look practically identical, right? But to a Cambridge examiner, oh, it's night and day. One is a top-band physics answer that locks in your grade, and the other, it's a critical error that literally loses you crucial grade boundaries. It really is that serious. And then we have this nightmare scenario. You know the feeling? You do the math, and your calculator spits out something like 1.23578. Listen to me. Writing this scary, unrounded string of numbers down on your exam paper is probably the single most painful learner mistake you can make. Why? Because it screams to the examiner that you don't actually understand the physical limits of the tools you're using. So why does ordinary revision fail to fix this? Well, because it falls straight into the standard revision trap. Look, students memorize formulas all day long, but they completely ignore how Cambridge examiners aggressively penalized missing units, rounding too early, or throwing in unjustified digits just because they happen to be on the calculator screen. We need a system to beat this. To beat the trap, we're going to use our 4-step Highmark framework. It goes like this. Step 1, concept. Step 2, evidence or data. Step 3, scientific reasoning. And finally, Step 4, examiner wording. We are going to use this exact framework to dissect every single measurement and calculation today. Let's get to work. Section 1, precision of measuring devices. Let's figure out what our tools can actually do. Okay, the source material gives us a strict, unbreakable rule here. Whenever you list your apparatus, you've got to find the smallest division on its scale. And here is the secret. Your precision is usually half of that smallest division. So think about a meter ruler. If it has a 1 millimeter division, your precision is half of that, meaning 0.5 millimeters. Or a thermometer with 1 degree Celsius intervals? Yep, your precision is 0.5 degrees. It's a really simple universal standard you can always rely on. And this brilliantly illustrates why the length of what you're actually measuring matters so much. Let's contrast these two. A measured length of 1 meter, which is 1,000 millimeters, right, gives you a precision of 1 part in 2,000. But if you measure just 1 centimeter, wow, your precision plummets to 1 part in 20. Basically, the precision becomes a much smaller, much safer proportion of your measurement the longer the length you are measuring. Make sense? Now, in just a moment, I'll reveal the ultimate examiner clue that changes your final answer completely. But first, you really need the framework that makes that clue absolutely obvious. If you miss this next step, the biggest trap in the entire syllabus is going to catch you off guard.
Section 2, the significant figures trap.
Let's quickly break down how to identify these figures because, well, they indicate exactly how accurate we think a measurement actually is. Take a number like 6.7. That has 2 significant figures. Simple enough. Now look at 0.235. That has 3 significant figures, with the 2 being the most significant and the 5 being the least significant. Now, for the absolute golden rule. If you only remember one thing today, make it this. Quote your answer to the smallest number of significant figures used in your calculation. I'm going to hammer this home, guys. Your final answer cannot physically be more precise than your least precise piece of raw data. It's impossible. So if you multiply a value with 2 significant figures by a value with 5 significant figures, your final answer absolutely must be quoted to 2 significant figures. But wait, what if they throw standard notation at you? Don't panic. It's actually super straightforward. Take 6.24 times 10 to the power of 2. You literally only count the digits before the power of 10. So we count the 6, the 2, and the 4. Boom. That gives this number exactly 3 significant figures. Easy, right? Section 3, Spot the Error Challenge. Let's see how sharp you are. All right, let's break this down. First, we have the flawed student answer, 1.235. So what exactly went wrong here? Well, they completely ignored the precision rules. They justified way too many digits, and honestly, worst of all, they totally left off the units. You can't do that. Now contrast that with the top band answer, 1.2 units. Perfection. It correctly applied the rules. If the lowest significant figures of the raw data was 2, they looked at the following digit in 1.235, which is that 3, and since it's under 5, they rounded down perfectly to 1.2. And they included the units.
If we channel the examiner directly, here is exactly why that top-band answer gets full marks. The examiner's feedback is wonderfully blunt. Never give more digits in a calculated answer than are justified by the apparatus and how it was used. That top-band answer correctly applies the physical precision limits of the original measuring device. They're basically telling the examiner, hey, I know my tools.
Section 4. The final missing piece, sources of error.
All right, here is the exact source material definition of error. Listen, every single measurement you take is an attempt to find the true value. But you have to understand and accept that perfection is literally impossible. Why? Because you are always subject to errors arising from the limitations of your apparatus, and, let's be real, you are always subject to errors in human experimental procedure. We make mistakes. Our tools aren't perfect.
But acknowledging that fact creates a massive, urgent, unresolved problem that directly threatens your marks in the practical paper. Think about it. If every measurement has errors, how do you handle anomalous data in practical investigations? If you can't identify and fix an anomaly, your entire experimental conclusion just completely falls apart. So let's summarize today's wins. We have successfully solved precision calculations and scale divisions. Awesome. We have solved significant figures and rounding rules. Fantastic. But that final piece? Identifying anomalies and practical improvements? That is a massive question mark right now, and mastering those practical traps in the next explainer is absolutely mandatory for your exam success. You simply cannot leave that gap open. Are you really ready to step into the exam hall knowing your practical data anomalies might sabotage your final grade? No way. To close this gap and secure those practical marks, you must click the next explainer on your screen right now. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Do not leave your final grade to chance. Click the explainer and I'll see